Hello, everyone. Good afternoon. So we are going to present an explainable AI algorithm for COVID-19 detection based on layer-wise relevance propagation. My name is Josh,
I'm Vedant.
I'm Tolope.
I'm Kriti.
and our advisor is Dr. Victoria Liu. So a quick overview of what we're going to go over today is an introduction, mainly looking at a background, convolutional neural networks, explainable artificial intelligence, and our objectives for this study. Our methods are going to be looked over deep learning models using X-ray image datasets and explainable AI methods, mainly layer-wise relevance propagation, LRP, and deep Taylor decomposition. Then, from these methods, we're going to find results and discuss these results. Lastly, having conclusion and what future work we are going to do next. So, let's start on our introduction. Um, in 2021, COVID-19 deaths significantly increased, which led to researchers and scientists devoting attention to it. Artificial intelligence, AI, and machine learning programs are introduced for more accurate results to compare to X-rays. They often operate as black box models, meaning that we don't actually understand how the algorithm works, so we can't really trust it. But to solve this issue, we can use explainable AI models, which allow the researchers to better understand the model and erase unnecessary biases and help the doctor perform a more accurate diagnosis. So, for our actual detection algorithm, we need to use a model. Our choice is a CNN or convolutional neural network. It's a type of deep learning model specifically designed for processing and analyzing visual data. A CNN applies convolutional filters to the input image, extracting local features such as edges, textures, and patterns. And now we're going to look at explainable artificial intelligence. So, explainable AI works with first having a training data that is used by an AI model, and we need to make sure that there is a validated performance. And now the explainable AI part works when we use interpretability models. These are different methods such as LRP and LRP. And with these models, we can have more trust, causality, informativeness, and fairness and transferability for humans to use and ensure that the model is accurate.
Okay, so these are some of the explainable AI algorithms that already exist. So there's Deep Taylor Decomposition, Deep Taylor Bounded, and LRP or Layer-Wise Relevance Propagation. And then there's different rules for them. They use different formulas to calculate the algorithms, and then these are some of them listed out here. So the objective of our research, the goal was to use explainable AI in order to understand a little bit more about why the AI model is making the decision that it is. So overall to gain insight into the decision-making process of the CNN. And we built the CNN using TensorFlow, and it classifies different lung X-ray images into either normal, viral, bacterial, or COVID-19. And then after that, we're trying to identify the different differences in the LRP rules. And then in the future, we want to extend our methodologies to find different applications for explainable AI, such as right now we're doing with COVID and pneumonia, but other applications like cancer and other diseases. So as far as our methods, we created the CNN using Python, using the TensorFlow Keras library, and we trained the CNN on 2 classes without COVID-19, that data set, as well as a 3-class data set. And the data set we got from Kaggle, so we found these X-ray images of both pneumonia and COVID, as well as healthy lungs on Kaggle. And then the explainable AI library is from Investigate. Okay, so a little bit more about layer-wise relevance propagation in specific. So LRP is just one of a lot of different explainable AI methods, and the goal again is to interpret the CNN's predictions, and it does this by redistributing the relevance from the output layer to the input layer. So essentially, it identifies like what the most important features of the image were that influence the CNN's decision, such as like the different pixels of the images. Um, and as far as the algorithm, it starts with the output relevance or the prediction score, and then it propagates it backward layer by layer, and it kind of decides like how important each part of the image was in the diagnosis. Okay, so deep Taylor decomposition. So this is a method that kind of builds on LRP. And in Deep Taylor decomposition, it breaks down the output decision of the deep neural networks into contributions of each individual input feature. And then each input feature is assigned like a relevance score that indicates how much it contributed to the final decision of the CNN. Yeah, so these are some of the images that were in our Kaggle data set. So you can see like the pneumonia lung on the left side, and then the COVID-19 X-ray, and then on the top right, you can see the normal X-ray.
So these are our results. So for the validation accuracy, for 2 classes and for 3 classes, the graphs look very similar. Over time, the accuracy is increasing for the models. And for the validation loss for 2 classes and for 3 classes, they both also look very similar. They also are generalizing to unseen data better.
Here's the
And then,
confusion. Oh, sorry.
oh, next. And for the confusion matrices of 2 classes, you can see that the purple boxes mean that there's misclassifications or errors, and the blue and the yellow boxes mean that there's correct classifications. And as you can see, the purple boxes have lower numbers and the blue and yellow boxes have higher numbers, which shows that it's very accurate and there's a higher number of correct classifications.
I can go into the performance metrics here. So obviously, instead of just qualitatively measuring the confusion matrices, we also wanted to analyze it using precision recall, F1 score, and accuracy. So we did this through first just looking at the true positives, false negatives, and true negatives. So obviously the true positives, it's when the model correctly predicts the positive class. So if the lung image displays pneumonia and the model correctly predicts that's pneumonia, that counts as in the true positive category. False positive is when it's normal, but when the model predicts that normal lung image, which does not have pneumonia, but instead predicts it as pneumonia, and henceforth, we use the following equation. So precision specifically analyzes the impact of false positives on overall model accuracy, recalls for false negatives in specific, and the F1 score basically balances precision and recall. And the F1 score is basically another version of accuracy, but it's specifically trying to look at the impact of precision and recall, specifically the impacts of the false positives and false negatives I mentioned, while the accuracy is trying to look at the holistic accuracy of the entirety of the model, not that in specific. So in total, here's a chart trying to display exactly what impact the precision, recall, F1 score, and accuracy did have. So for the 2-class model, we see really high accuracies of 95.4%, even for the 3-class model. And here's the precision and recall. Once again, the F1 score is just balancing the results of the precision and recall. So obviously this is really high accuracy rates, but especially in something that's like a healthcare related task, increasing it only makes it better. Yeah.
So here we have heat maps for a specific chest X-ray, and all these heat maps are slightly similar, but they have some differences. For illustration, LRP flat, you can see that the whole thing is highlighted, which is not correct for identifying pneumonia. So that's obviously wrong. But in rules such as deep tailored bounded, you could see that the edges of the lungs and the diaphragm are correctly highlighted, which is important for classifying pneumonia. So in this case, we have a chest x-ray of a 65-year-old male, and this patient was tachycardic, but maintained oxygen saturation on low flow. And in this x-ray, we could see that there's coarse, patchy opacification of both lower zones, which appear inflammatory in nature. So this patient was diagnosed with COVID-19. So the explainable AI analysis of deep Taylor decomposition, you could see the heat maps of deep Taylor analysis compared to the original chest x-ray. And the model predicted COVID with 1.0 probability, but we decreased the validation image size to 64 by 64 to help decrease computational power and to keep visual interpretability. So these are more LRP results, specifically LRP alpha 2 beta 1 and LRP sequential preset A. We could see the blue relevance and the positive relevance and the negative relevance, which is marked blue and red. And we circled parts that were important in identifying the COVID-19, which was mainly the diaphragm and the outer edges of the lungs. And next we have the LRP alpha beta and the LRP Z plus. We could see that they don't have negative relevance, which is the blue highlights, but we could see that they have concentrated, the positive relevance is concentrated in certain regions that correspond to the areas of interest marked in the original X-ray. And although LRP alpha beta and LRP Z plus look very similar, we could see that LRP Z has a higher contrast between high and low relevance regions, and it leads to clearer distinction between areas of interest and surrounding areas.
We also wanted to figure out between Deep Taylor and Deep Taylor bounded rules, trying to find some differences there. For Deep Taylor in specific, which is shown on the right over here, there's a really good mapping of relevance with really good highlighted portions. But as Lupe mentioned, there's less contrast, which makes it a little difficult to specifically identify and interpret the specific regions of interest which influence the overall results, specifically in the X-ray image. For Deep Taylor bounded, it's similar relevance mapping in terms of the highlighted portions and circled regions of which specific pixels are highlighted, but there's more contrast when compared to Deep Taylor, which makes it much easier to visually identify the areas that contributed most to the decision, in this case, or pneumonia. For LRP Z plus in specific, it makes that way more effective for interpretability compared to Deep Taylor and Deep Taylor bounded, specifically for this contrast region.
What's the concentrate? What is the thing in the upper left in the, basically it looks like the shoulder.
Yeah, it's just the highlighted region that it thought was the reason like why it concluded pneumonia or COVID in that case.
Okay.
So as the conclusion, just analyzing the results and differences between the specific LRP rules, we found that for LRP alpha 2 beta 1, the areas of relevance in that corresponded reasonably well with the actual results in the original X-ray and the radiologist reports that we looked at analyzing what specific abnormalities existed that created their results in terms of COVID or pneumonia diagnoses. However, the relevance there was scattered in terms of where the highlighted regions were and weren't very focused, specifically in the lower parts of the run, where most of the pneumonia diagnoses are made based on the lower opacifications. For LRP sequential preset A, that heat map had a much stronger alignment with the regions of interest in the original X-ray image, which meant that the relevance areas or highlighted areas were more localized and specifically concentrated around the regions that made the radiologist decide in reality which one is the reason why it's pneumonia or COVID or the diagnoses. For LRP alpha beta, It was a reasonable mapping of relevance, but there wasn't very contrast, as we mentioned before, which makes it really hard to specifically identify what part of the heat map or what part of the lung is why the diagnoses took place. For LRP-Z+, it's similar relevance mapping, but there's much more contrast, which makes it very much easier to identify the areas that once again create that result. For Deep Taylor and Deep Taylor bounded, they're a little more computationally intensive, but it's much more distinct visualization of the specific relevant regions for the overall diagnoses, which makes it much easier to interpret those areas that correspond to the overall model prediction. In terms of future work, we're trying to take it in two major directions. First can be real world data validation. Obviously, we looked at real world data that was used in terms of lungs, but the model does perform well on these types of data sets. For future studies, we would use this explainable AI, convolutional, as well as a convolutional neural network for more like diverse patient data and real world hospital data sets. So just extending the data sets that we're looking at to get a more like total perspective on what data we're looking at and how we can analyze it. The second thing is the relevance map evaluation. So instead of just qualitative metrics to analyze heat maps and the differences between specific rules and their corresponding heat maps, more quantitative metrics to evaluate that. So for example, we could do some overlap with the radiologist annotations, but instead of qualitative metrics, they could be quantitative ones. The overall goal is just find more concrete, definitive contrast between different LRP rules to analyze which works the best in which specific situation. Obviously, we'd love to thank Dr. Liu and ASDRP for the opportunity to conduct this research. It's been a really great experience so far. Here are some of our references. And yeah.